This is our last lesson in Chapter 8. We're going to look at work, motion, and mixture problems today. Here's our first example using a work rate. If Sean can mow a lawn in 4 hours and Tony can mow the same lawn in 5 hours, we want to know how long would it take them working together with 2 lawn mowers to mow the lawn. So here you can see my equation is set up. If Sean can mow the lawn in 4 hours, he mows a fourth of it in 1 hour. And Tony takes 5 hours, so he can mow 1/5 of it in 1 hour. If they work together, they mow 1/t of the job per hour. Now we can write that equation. Also, motion problems, we know that distance is rate times time. It's possible to write a fractional equation for time and for rate. This is our main formula that we've known since elementary school. If distance is rate times time, you can divide by rate and get a name for time. Time is distance over rate. And similarly, we can get a name for rate. Rate is distance over time. So let's look at our first problem. We want to complete the table here. Chad can load a truck in 24 minutes. So he does 1/24 of the job in a minute. His time is T. So if we multiply work rate, this is our work rate here, times the time, we get his work done, T over 24. James takes 40 minutes to load the truck, so he does 1/40th of the job in a minute. This is his time, so time over 40 is the work done by him. If we think about it verbally, Chad's work time plus James's work time gives us the total job. So let's put that together in an equation. This is the work time right here. So Chad's work time is T over 24. James's work time is T over 40. And together they complete the whole job. So we need the least common denominator between 24 and 40. And our least common multiple is 8 times 3 times 5. So 8 times 3 times 5 is 120. If I multiply the left and the right by 120, 24 goes into 120 5 times. And then 40 goes into 120 3 times. 1 times 120 is 120. So 8t is 120, and t is 15 minutes. So together they work 15 minutes. Here's one for you to try. Morgan takes 6 minutes to weld a frame. With the help of Alec, the job can be done in 4 minutes. How long would it take Alec to do the welding job alone? So Morgan does 1/6 of the job in 4 minutes, and 4 over 6 is 2/3. So we could reduce 4 over 6 down to 2/3. Alec does, we don't know, 1 over t in 4 minutes, so he needs 4 over t to do the job. If you think it through verbally, Morgan working plus Alec working is the whole job in 4 minutes. And we want an equation for that. So 2/3 plus 4 over t gives me the whole job. Our least common multiple is 3t. Multiplying the left and the right by 3t, 3t divided by 3 leaves us 2t, and t goes into 3t 3 times. 3 times 4 is 12. So 2t plus 12 is 3t, and t is 12. So Alec can do the job by himself in 12 minutes. Example 3 is another rate problem. Train A has a speed of 14 miles an hour, faster than the speed of train B. So I want to call train B R. R is the rate of train B. And train A is 14 miles an hour faster, so that rate is R. Train A travels 400 miles in the same time that it takes train B to travel 330 miles. We want to find the speed of each train. So train A is 400 equals rate times time. Train B, distance, equals rate times time. And we want to find the speed of each train. Well, if distance is rate times time, then the times are the same, so time is distance divided by rate. In this way, we can set up the equation to be distance divided by rate. So the distance is 400 divided by rate. So 400 divided by rate is equal to 330 divided by rate. Solving for R, 400R equals 330 times the quantity R plus 14. So 400R is 330R plus 330 times 14, which is 4,620. Solving for rate, R is 66 miles per hour. Going back to answer the question, the speed for train A is 66 plus 14. So the speed for train A is 80 miles per hour. And the speed for train B, we solved, which was R, is 66 miles per hour. Here's one that's similar to example 3. You can solve for yourself and then come back to check your work. An airplane flies 1,062 miles with the wind. In the same amount of time, it can fly 738 miles against the wind. The speed of the plane in still air is 200 miles per hour. So 200 plus W, we're going to let W represent the speed of the wind. And then against the wind would be 200 minus W, and they travel, this plane travels at the same amount of time. If we solve distance equals rate times time, and times are the same, we're doing the same thing, distance divided by rate. So distance of 1062 divided by the rate, 200 plus the wind, is equal to distance 738 divided by the rate against the wind. Solving for W, 1062 times 200 minus W is equal to 738 times 200 plus W. This is 212,400 minus 1062W is equal to 730, oh, I'm sorry, I got to multiply. 738 times 200, which is 147,600 plus 738W. So collecting like terms, this is 1,800W. If we add this 1062 to the 738, and 147,600 minus 212 is 64,800. Dividing by 1,800, the wind is 36 miles per hour. So the speed of the wind is 36 miles per hour. In example 5, we're going to consider some mixture problems. Some real-world mixture problems involve finding weighted averages when some element carries more importance or weight than any other element. Often the problems involve percentages, so we can create a table that will help us organize the information and understand the problem. In this example, Jennifer is a pharmacist and needs to dilute an alcohol solution. She has an 8-liter container, so the liters of solution, she has 8 liters of 9% solution, 8 liters. How much water would she need to add to the container to get a 5% alcohol solution? So let's let X be the amount of water that she's going to add. X is going to stand for the amount of water. So she's got 8 liters and she's going to add some water to get it down to a 5% solution. And I'm thinking that the liters of the 9% solution has to be the same as the liters of the 5% solution. So she has 0.09 and 0.05. So 0.09 times 8 and 0.05 times 8 plus X have to be the same. These two need to be the same. So if she has 0.09 times 8 and 0.05 times 8 plus X, let's first multiply through by 100, and that will change the decimals to be 9 times 8. So we'll get 72 here. And on the right side, that 5% is going to turn out to be a 5 times 8 plus X. So we'll distribute and get 40 plus 5X. So 5X is 32. And 32 divided by 5 is 6 4/10 liters of water. So she'll use 6 4/10 liters of water added to that 8 liter, and then she'll have a 5% solution. Here's one more mixture problem. A chemistry student needs to mix an 18% solution with a 45% acid solution in order to end up with 12 liters of a 36% solution. How many liters of each acid solution must be used? So we're going to call X the amount of the solution for acid 1, and we want to end up with 12 liters at the end. So if we end up with 12 liters at the end, this has to be 12 minus X for acid 2. And converting 18% to a decimal, that's 0.18 times X, so I'm multiplying down this way. And 45% is 0.45 times 12 minus X. So we're going to do the same thing here, 12 times 0.36, or 36%. So we've got, the situation would be, we're going to take acid 1 and add it to acid 2, and it'll give us the final. You see it that way? We've got acid 1 plus acid 2 will give us that final amount. That's 12 liters at 36%. So we're looking across this bottom row, 18% of X and 45% of the 12 liters minus X is going to give us 12 liters at 36%. So collecting like terms and solving for X, 12 times 45% is 5.4 minus 45%, and 12 times 36 is 4.32. So if we subtract 4.32 from 5.4, we're going to get 1.08, and 18 minus 0.45, and then putting that on the other side would give us 0.27x, and 0.27 goes into 1.08. Oh, a nice even number of 4. So going back up here to row 1, we want 4 liters. We want to use the 4 liters for acid number 1, which is the 18%. And we want to use 12 minus 4. We want to use 8 liters of the acid, that's 45%. And that will end up giving us 12 liters, that's 36%. This is our last problem. We have 2 pipes that carry water to the same holding tank. Pipe A can fill the tank 3 times as fast as pipe B. So pipe A works faster than pipe B. We'll call pipe A fast and pipe B slow. Together they can fill the tank in 24 hours. So the time is 24 hours. If we say the work is done by pipe A at 1 over x, then it's doing the total job in 24 over x, because it works 3 times as fast as pipe B. So pipe B is slower, 1 over 3x. So pipe B is doing the job in 8 over x. The equation we need to do the whole job is pipe A and pipe B gives me the whole job. So 32 over x is the entire job. X is 32 hours. So putting all of that into words for our solution, pipe A can fill the tank 3 times as fast as pipe B. So pipe A takes 32 hours to complete the job, doing it alone. And then for pipe B to do the job, it's going to take pipe B 32 times 3, so it's going to take pipe B 96 hours to do that job alone. And that is the end of our chapter 8.